Hi everyone, this is going to be a quick lecture where we do a rundown of all of the organic functional groups that you're going to have to know. So when we say functional groups, what exactly do we mean? Well, when certain atoms are bonded together in a specific arrangement, they will behave similarly and undergo specific chemical reactions. So that arrangement of those atoms is what the functional group is. And each functional group will have its own properties, regardless of what other atoms are present in that molecule. And so when we look at a molecule, we can kind of pick out these functional groups or these arrangement of atoms, and then later we'll learn all the individual functional groups separately. So what you're going to end up having to do in this chapter is essentially make flashcards and memorize the different names and structures of the major functional groups. So we have three molecules on the bottom here, just for an example. Morphine, which is an opioid analgesic, so that's the drug class. It has a few functional groups that I can see right off the bat. It has this nitrogen that's bonded to 3 carbons, 1 carbon here, here, and here. This is called an amine, and because it's bonded to 3 carbons, it's called a tertiary amine. Here we have an OH group and another OH group. Both of those are called alcohols. That's one type of functional group. Here we have an oxygen that's bonded to 2 carbons. That's called an ether. And another one in this morphine molecule is this ring right here, which is called an aromatic ring. And so when we look at a molecule, we can kind of pick and choose these different functional groups, and these are different sites of reactivity that could react with different things. Another example is amphetamine. This is a phenethylamine drug class, and we have another aromatic ring right here. Here we have an NH2 group, which this is also an amine, but because it's bonded to only 1 carbon and not 3, this is called a primary amine. And so we use 1, 2, or 3 with that little superscript 0 symbol there to represent primary, secondary, or tertiary for certain functional groups. And then the one on the far right is Lipitor, which is an HMG-CoA reductase inhibitor, also known as a statin. And this guy has a ton of functional groups on it. One that we haven't looked at yet is at the very right end, where we have a carbon double bonded to an oxygen, which is also double bonded to an OH group. This is called a carboxylic acid. And we have a couple alcohols. Here's an OH group, here's an OH group. We have a lot of aromatic rings. And another one is this arrangement of atoms where we have a carbon double bonded to an oxygen, and that same carbon is bonded to a nitrogen. This is called an amide. So these are just some examples of a few of the common functional groups that we're going to learn this year throughout Organic 1 and Organic 2, and then all the individual reaction mechanisms that they undergo. So this was just an example of using some molecules and picking and choosing and identifying the functional groups that are present within them. So next we're going to go through the whole list of them and what they look like and how we name them. Okay, so as we go through all of the different types of functional groups, the things that you want to think about when we are talking about them is what is the most electronegative atom present and what is the most electropositive atom present, if there is a difference between them. So who would get that delta positive or partial positive charge, and who would get that delta negative, which meant partial negative charge. Out of the functional groups, think about what ones would be capable of hydrogen bonding. Remember, hydrogen had to be bonded directly to an oxygen, a nitrogen, or a fluorine. And then what functional groups are polar and will be capable of dipole-dipole interactions. So later we'll look at a polarity chart of them, but you want to keep all this stuff kind of in the back of your mind as we're going through what these functional groups look like, and then talking about, some of their naming suffixes. So a functional group can have a suffix or it can have a prefix, and sometimes there's only one or the other, and sometimes there's both. And how we use them would be depending upon if that functional group is being named as the parent of the molecule, we would use the suffix. If it's mixed with a bunch of other functional groups, it might end up not being the parent, and a different one could be the parent, and we would have to use a prefix to name it. Usually when we learn naming different classes of functional groups, I won't try to mix too many. We'll learn how to mix a few, but that means that a lot of times we'll be using the suffix usually, until at least we build up some more background knowledge. So starting with the simplest, which isn't even actually really a functional group, but an alkane, which is what we were talking about in this chapter, that has the ending or the suffix ane, that's where you have all single bond carbons. And whenever I use R, or you see R in your textbook, an R group just means any carbon arrangement. So I could have drawn a chain that was 2 carbons long, 3 carbons long, or 20 carbons long. That R group doesn't really mean it's part of the functional group, so it's not the important part of the molecule. It could be any carbon chain. So an alkane is a fully saturated hydrocarbon that contains all single carbon and hydrogen bonds there. So each carbon in an alkane has sp3 hybridization, and it's tetrahedral arrangement, so bond angles are about 109.5 degrees apart. The next group of molecules, when we start learning mechanisms that we'll learn, are called alkenes. Alkenes have the suffix ene. So it's important that you learn all of your naming rules for alkanes, because they're only going to get built upon and expanded when we learn alkenes. Alkenes are similar to alkanes, except for they contain at least one carbon-carbon double bond. And that carbon-carbon double bond doesn't have to be at the end of the molecule. It could be terminal at the end, or it could be internal and in the middle of the molecule. And so my alkene could have 8 carbons long. It could just be a simple alkene that has only 2 carbons. And then it would have the rest of the bonds filled with hydrogen. With an alkene, we say that the molecule is unsaturated. And this is something we'll talk about more in the alkene chapter, but unlike an alkane that was fully saturated with hydrogen, an alkene has a degree of unsaturation where now that double bond lives. So for it to be an alkene, that molecule would contain at least one carbon-carbon double bond. Next we have an alkyne. The suffix for alkynes, the ending is yne or ine. An alkyne is where we have a carbon-carbon triple bond. So when you're looking at this, it looks a little funky, but there's a carbon here and there's a carbon here. And so then there's one here, and then the R group could continue as far as it wants to go. So you could have an alkyne that just has 2 carbons, which that would look like this. And we don't usually show these carbons, but I'm just drawing them right now. And that alkyne would be named acetylene. That's essentially like a common name for it. But you have 2 carbons that are triply bonded together. So in order for that alkyne functional group to be present, you at least have to have that. And notice how it's shown being linear. That's because each of those carbons are 180 degrees apart, and each of them is sp hybridized. So same here, sp overlap there. Alkyl halides, these are not high priority, and so they're usually never named as a suffix. They're always named with their prefix, and you saw this when we were doing some naming. So alkyl halides could be something like a fluoro group, a chloro group, a bromo group. They're halogens, so generically we have some carbon chain, some R group, and coming off of there we have a halogen where X is our halogen. So we could have fluoro, chloro, bromo, iodo, fluorine, chlorine, bromine, or iodine. And when we're looking at our halogens, we can have a few different degrees of them depending upon how many carbons they're bonded to. So in this example that I drew, our carbon right here that our halogen is coming off of is bonded to 1 carbon here and 2 carbons here. What's not being shown is we have to know that there's 1 hydrogen right here. So in this example, we have 2 carbons that are bonded to what's known as the alpha position, which is the position that's directly attached to our halogen. So this is an example of what's known as a secondary alkyl halide. For example, if we were to have had something like this, we have an R group, and then we have our halogen right here. Well, on that alpha position, which is this one, there are 2 hydrogens coming off here. And there's only 1 carbon, which is the R group, that's directly attached to that alpha position. So this is an example of a primary alkyl halide. And we could actually specify what that halide is. So is it a primary bromide, primary alkyl bromide, primary alkyl chloride, etc. So I'm just using X generically right now to represent any alkyl halide. So we could have a secondary one, a primary one, or we could have an example where we have lots of carbons. These could all be different R groups coming off, any amount of carbons coming off of that alpha position. So here's our alpha position where our alkyl halide is bonded to. And then we want to look at the number of carbons directly attached to that alpha position. We got 1, 2, 3. So this is an example of a tertiary alkyl halide. So those chains that I drew the length, they don't matter. I could have just abbreviated my alkyl halide just as well as this. 3 R groups, could be the same, could be different, and then an X coming off there. That would also represent a tertiary alkyl halide as well, because we don't care about what those carbon chains are. They're not important. Next functional group we're going to look at is an alcohol. An alcohol is where you have an OH group coming off of your carbon chain. If the alcohol is the parent molecule, the suffix is OL, and that would occur at the end of the name. If another functional group was the parent and the alcohol was just named as a prefix or a substituent on that other main chain, we call it a hydroxy group. So just like with our alkyl halides, we can have 3 degrees of alcohols. So for example, if we have an R group of some sort, some carbon chain, and that's bonded to our alcohol, this would be our alpha position. And coming off of our alpha position here, we have 2 hydrogens. Our alpha position is only bonded to 1 other carbon. So this would be a primary alcohol. Next, we could have an example where we have 2 carbon chains coming off of our alpha position. And what's not shown, what's not drawn in, is there's 1 hydrogen there. So off of our alpha position, we have 1 carbon, 2 carbons. This would be a secondary alcohol. And lastly, we could have 3 different R groups, or 3 of the same R groups, coming off of our alpha position. So here's our carbon, here's our alpha position, that's the spot directly bonded to the oxygen of the alcohol. Notice that carbon has 4 bonds, so there's no hydrogens. This is an example of a tertiary alcohol. We got no hydrogens there, and if we count our carbons around our alpha position, we got 1, 2, 3. So for alkyl halides and alcohols, how you figure out primary, secondary, or tertiary is the same. You look at how many carbons are bonded to that alpha position. That's going to change a little bit when we look at our next functional group, which is an amine. Amines have the suffix, when you're naming them, the same as the functional group. They're also called amines. If we have to name an amine as a prefix, as a substituent on a chain, we call them an amino group. And they also come in 3 flavors, primary, secondary, or tertiary. But how we determine that is just a little bit different here. So imagine we have some R group, and then coming off of our amine, which is an NH2 group, or NHX, I'm going to say for now. In this case, we're not going to look directly at that alpha carbon. We can kind of, and however you want to think about it, I guess. The number of hydrogens usually is what I hone in on. Here we have 2 hydrogens directly bonded to our nitrogen, and we have 1 carbon attached here. So we have 1 carbon attached, 2 hydrogens. This is an example of a primary amine. If we have 2 carbons directly attached to our nitrogen, so maybe we have some R group here, and then we have another R group here, that would leave us with 1 hydrogen bonded to our amine. So 1 hydrogen here. Here we have 1 carbon, another carbon. This is an example of a secondary amine, where we have 2 carbon chains coming off of that nitrogen. And you gotta kind of start to recognize what's not being shown on the nitrogen. It doesn't have a formal charge indicated, so if it doesn't have a formal charge, this is a trivalent molecule, so there's a lone pair on that nitrogen that's not going to be shown every time. And then lastly, if we have 3 R groups or 3 carbon chains coming off of our nitrogen here, it's going to have no hydrogens on it, and we got 1 carbon, 2, 3 directly bonded to that nitrogen. This is a tertiary amine. So we're not looking at how many carbons are on an alpha position per se. We're looking at how many carbons are bonded to the nitrogen, or you can think about it like how many hydrogens are bonded directly to that nitrogen when determining if it's primary, secondary, or tertiary for the amine. Next, we have a nitrile, and this is another nitrogen-containing functional group. The suffix for nitrile is nitrile. Sometimes it's written as O-nitrile, and we will cover these later. If it's listed as a prefix, it's called a cyano group. So a nitrile is when you have your carbon chain, and it's bonded to a CN group. And what that CN group really looks like is you have carbon and it's triply bonded to nitrogen. So you can draw it shorthand like this and just write CN, or you can write it out longhand and show that triple bond between carbon and nitrogen. Either way, you should know that that is what that really looks like if you were to write out the full structure. Next and last on this page, we have a functional group called an imine. An imine is where you have a carbon chain and you have a carbon double bonded to a nitrogen. So that part of it is what the functional group is, not that R group. You've got your carbon here, it's not shown because we're using line bond structure. So carbon is double bonded to nitrogen, and then nitrogen is trivalent, so it has 3 bonds and it has a lone pair of electrons on it. And so the other bond to nitrogen would be with hydrogen. The suffix for naming imines is the same as the name for the functional group, I-M-I-N-E or imine. If we named it as a prefix, it's called an amino group, not amino like an amine, imino with an I. Now we're going to look at some oxygen and sulfur containing functional groups. And oxygen is right above sulfur in group 6A on the periodic table. So first we have ethers, which an ether is a functional group where you have two carbon chains flanking an oxygen. And oxygen, we know, has two lone pairs of electrons on it. And so however long those carbon chains are, it doesn't matter. You could have a single carbon chain, or you could have a 10 carbon chain on each side, or they could be different carbon chains. The part of this that is the ether is the fact that we have this going on. So when we name ethers, the ending is ether. And if we name an ether and it's not the parent, and we're naming it as a prefix, it's called an alkoxy. And the L part of that, the alkoxy part of that, will change depending upon if it's a methoxy, an ethoxy, a propoxy. So that would depend on the length of the chain that's attached to the oxygen. So that prefix is really generic when we say an alkoxy group. What we mean is it's some kind of a oxygen with a carbon group on it, and that carbon group will actually have some amount of carbons, 1, 2, 3, 4, however many. Peroxide, you've probably heard of peroxides. The one you would have been familiar with would be hydrogen peroxide in the little brown bottle under the medicine cabinet. So if you can think of hydrogen peroxide, what makes this a peroxide really is this part of it, that oxygen-oxygen single bond. So we can have lots of organic peroxides that are not considered hydrogen peroxide by changing these hydrogen groups here for R groups. So it's same structurally here. We contain this peroxide bond, but now those R groups could be anything. And peroxides, when we look at them, we'll be learning about radical reactions, because this peroxide bond right here, that oxygen-oxygen bond, is rather weak, and it can break really easily, even on its own almost over time. And it undergoes a type of cleavage where we'll end up seeing one electron end up going to each of the oxygens and forming something known as a radical. So that's why you keep your hydrogen peroxide in a brown bottle and away from light, because that peroxide bond will break and essentially it will decompose over time, and stuff like light and radiation can speed that up. So that's why they put it in the brown bottle. But even without, it hitting the light and it being in a brown bottle, you still have to replace it every so often because it'll still just go bad over time. We don't have a suffix for peroxide, but if we were naming it with a different functional group being the parent, it would be called a peroxy. Next we have thiols. Thiols are where you have some carbon chain bonded to an SH group. So this part of it right here, that's the thiol part. We have a sulfur bonded to a hydrogen. Suffix is the same as the functional group name, thiol. And if we were naming it as a prefix, we would call it a thio. So just drop the L. Next we have a sulfide, and a sulfide is basically an analog to the ether group that we saw at the top. We have some R groups and they're flanking a sulfur. So like I said, sulfur is right below oxygen on the periodic table, and it does a lot of reactions similar to oxygen. So when we learn ethers and thiols and sulfides, we'll learn a lot of those at the same time because they undergo very similar types of reactions. So a sulfide, when you're naming them, if it's the only functional group, that would be the parent, and it is called a sulfide, same as the functional group name. And if we're naming something else as the parent, and we're using the prefix part, it's an alkyl thio. So just like with the alkoxy, the alkyl part here can change. Is it a methyl thio? Is it an ethyl thio? What is the alkyl group that's attached to the thio part? We would have to indicate that in the nomenclature. So this part of it is the sulfide part. Just like we can have sulfides, we can actually even have disulfides. So if we have an R group and then two sulfurs together, this functional group right here is called a disulfide, and you may have even heard of disulfide linkages or disulfide bridges when you were studying biology, if you've taken any biology. We won't have a prefix for that, but the suffix is disulfide there. Sulfoxide group is similar. It's another sulfur-containing functional group. And we have a sulfur that has a double bond to an oxygen, and then it's attached to some carbon chains. So right here is the sulfoxide part of this. When we name sulfides and ethers, when we learn those, they're going to be very straightforward because a lot of them have a suffix that's exactly the same name as the functional group. So that's why if you know all the functional groups right now, it'll make your naming life a lot easier down the road. So sulfoxide has a suffix sulfoxide, has a prefix sulfoxy. We probably will never use that though. And then the last sulfur-containing functional group that we're going to cover is called a sulfone. So it's our generic R group here. We have a sulfur, and that has 2 double bonds to oxygen. So this part of it right here, that's our functional group, that's our sulfone. Just like sulfoxide, the suffix matches the name. So sulfone is the name of the functional group, and it's the suffix. If we did want to name it with a prefix, it's a sulfonyl. For a lot of these, you won't use the prefix very often because I try to keep the naming simple as we can by not mixing too many functional groups together. And last one on this page here, we have aromatic. And we'll spend a whole chapter on aromatic compounds eventually because they're actually a lot more sophisticated than what we're saying right here. Right now, when we're looking for aromatic compounds, I want you to kind of focus on a benzene ring. And that's what this is. When you see this 6-membered ring with alternating single and double carbon bonds, because remember you got carbon here, 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 and here, this is called benzene. And this is just one type of aromatic compound. There is a whole bunch of other aromatic compounds, and they kind of have their own reactivity, their own reactions, even their own naming rules. So that'll be something we cover in depth when we do aromatic compounds. But when you see a benzene ring for now, you can circle that and call it aromatic. Next, we're going to shift gears and focus on functional groups that contain a carbonyl. And a carbonyl is a carbon double bonded to an oxygen. So all of these functional groups that we're going to go through in the second half have a carbonyl within them, and it's part of the functional group. First, we'll look at an aldehyde. An aldehyde is where you have some R group, and then you have your carbonyl, and then on your carbonyl carbon, which is this one, it's directly bonded to a hydrogen here. So that's what makes it an aldehyde, is that carbonyl carbon is bonded to a hydrogen. So this whole part of it right here is the functional group. The suffix, when we're naming aldehydes, is they end in al, so Al. And similar to aldehydes is ketones. And actually when we learn reactions and properties, we learn ketones and aldehydes together because they do a lot of similar things. So the difference is a ketone is not bonded to a hydrogen right here off the carbonyl carbon. It's bonded to another carbon chain or another R group of some length. Could be the same as the first R group, could be different. So the ketone part of this, the functional group, is just the carbonyl. So essentially just having a carbonyl in a compound is a ketone when it's just flanked by 2 carbons on either side. The suffix for ketones is -one, O-N-E for the ending. Next, we have carboxylic acids. I notice sometimes they just call them acids. That's not formally correct. They are called carboxylic acids. And here we have an R group, and then we have our carbonyl carbon. And what's next to our carbonyl is an OH group. So this hydroxyl group has to be directly bonded to the carbonyl carbon. And together, the whole thing is a carboxylic acid. So we would not label this as an alcohol. because it would be an alcohol if it did not have that carbonyl there, but it does. So we take that as a whole, that piece as a whole, and that's together a carboxylic acid. And the suffix is oic acid for naming it. And lastly, we have an ester. So an ester is kind of similar to an ether. It's an oxygen-containing functional group, but we have our carbonyl, where we have our carbon double bonded to our oxygen, and then that is attached to an oxygen, which is then bonded to some other R group. So similar to a carboxylic acid and similar to an ether. What's different compared to our carboxylic acid? Well, instead of it being bonded, our oxygen, to a hydrogen, it's bonded to another carbon chain of some sort here. So this whole part of it right here, that's going to be your ester group. Those two R groups could change. The suffix is O8. That's our ending for naming esters. Next we have an amide. An amide is similar to an amine, and if you remember, an amine was a nitrogen-containing functional group, only our amide has a carbonyl in it, so C double bond O. So we have 3 classes of amides, just like we had 3 classes of amines, depending upon how many carbons are bonded to the nitrogen. So, for example, if we have some R group, and then we have our carbonyl carbon, and then off of our carbonyl carbon we have a nitrogen, and let's say our nitrogen is bonded to 2 hydrogens, so NH2 there. Looking at our carbonyl carbon, that's the only carbon that's directly attached to the nitrogen. So this would be an example of a primary amide. We got 1 carbon, and that is the carbon of the carbonyl. If we compare that then, we could have our carbonyl carbon, we could have our nitrogen, and maybe we have another carbon chain coming off of our nitrogen, and then just 1 hydrogen coming off. So this would be an example of a secondary amide. If we count our carbons, we got 1 here that's attached to our nitrogen, and another here. So 2 directly attached to that nitrogen. It's a secondary amide. And lastly, we could replace all the hydrogens with carbon chains. So we have our carbonyl, nitrogen, and we got an R group here and an R group here. So off of our nitrogen, we got 1, 2, 3 carbons. This is our last one, tertiary amide. And so the amide functional group part of this that we're kind of like honing in on would be this nitrogen that's directly next to that carbonyl carbon. So that part of it is the amide. You can see it can change between primary, secondary, or tertiary, but that doesn't really affect the reactivity. What affects the reactivity is having that nitrogen right next to the carbonyl. Next we have acid chloride, but really this could be acid halide. You could have acid chloride, acid bromide. We'll just write it out like it's acid chloride right now. And we could have something like this, some R group bonded to our carbonyl carbon, and then off of our carbonyl now we have a halogen, so chloride. The ending when it's like that is oil chloride, so OIL. And this part of it right here is that functional group. That's the acid chloride. This is what an acid bromide would look like. R group, carbonyl, and then a bromo group directly attached to the carbonyl. So right here, this is an acid bromide. And the ending would change a little bit. The suffix, if we were naming that, it'd be OYL, oil, bromide. And lastly on this page, we have acid anhydride. So the word anhydride means without water. So really what an acid anhydride is 2 carboxylic acids that came together and they were dehydrated, so water was removed, and they form this anhydride molecule. So if we have an R group, and then we have our carbonyl, off of our carbonyl we have an oxygen, and then we have another carbonyl group. And the R chains could be symmetrical or unsymmetrical on either side. But this part of the molecule, right here, those two carbonyls with the oxygen in the middle, that is the anhydride part. So you can almost see how it looks like if you had a carboxylic acid and you had another carboxylic acid. And you brought those together and you removed H2O, how you would be left with that acid anhydride. So essentially a dehydration reaction, or different dehydrating reagents are useful for reacting with carboxylic acids if you want to make an acid anhydride. The suffix, the naming suffix, is oic anhydride. So when we name carboxylic acids, our suffix was oic acid often, and when we name them for anhydrides, we switch it to anhydride, oic anhydride. So that was it for all of our functional groups. I highly suggest you make a flashcard for them and you put the name on one side and then you draw a picture of the functional group, the important part of it, on the other, and so then that way when you identify it, you can name it, and from the name, you can draw it. I also posted a link on Blackboard that goes to a website that shows the ranking of the polarity of the functional groups. So you can kind of get an idea of what functional groups are more polar than others. A lot of them have some polarity, and it's definitely going to depend upon the electronegativity of the atoms. So for example, you might remember we used partial positive and partial negative. So that was the lowercase symbol for delta, the Greek symbol for delta, and that meant partial. Another way that you will see people represent a dipole is by using a dipole arrow. So it will point towards the more electronegative atom, and there's an end that crosses at the more electropositive atom. So they both indicate the same thing. So when you look at these polarity patterns, you can see how the arrow is pointed. For example, starting at the top with the aldehyde, carbon, and then oxygen. So we learned that carbon-hydrogen bonds are essentially nonpolar, but carbon-oxygen bonds are definitely polar. So in this one, the carbon's partially positive, the oxygen's partially negative. So it's pointing towards the oxygen in terms of the dipole, because that's the direction of the polarity in that molecule. And would this molecule exhibit hydrogen bonding? We see this hydrogen here, but the answer is no. It's just going to have dipole-dipole interactions because that hydrogen is not bonded to oxygen or nitrogen or fluorine. That hydrogen is bonded to the carbon of the carbonyl. So no hydrogen bonding in an aldehyde. A ketone follows the same polarity pattern as an aldehyde. So typically you're going to see that the carbonyl carbon is partially positive, and then the oxygen is the more electronegative one. So you can see that for all of these carbonyl ones. For carboxylic acid, it's got polarity going the other direction too. So it's got it going towards the carbonyl oxygen, and then the oxygen that's singly bonded to that carbon. So you're going to want to check out these polarity trends and check out that website to see the ranking of these different functional groups, where they fall on the polarity spectrum. You'll see that things like amines and amides that contain nitrogen are extremely polar. They're some of the most polar functional groups. So next, let's go through and do an example where we circle, so we identify all the functional groups, we label them with their correct spelling and their correct name, and any common alkyl groups that we find as well. So alkyl groups could be things like ethyl groups, propyl groups, sec-butyl groups. We just want to practice using some of those common names of functional of alkyl groups as well. So starting kind of in the upper left here, we got this arrangement of atoms, which this is called an acid anhydride, where we have two carbonyls and they're flanking that central oxygen. Next to it on the right, this NH2 group. So we have nitrogen that's bonded to one carbon there, and it has two hydrogens. That's a primary amine. So you want to specify if it's primary, secondary, or tertiary if it has that. Right below that, I see we have a carbon-carbon double bond. That's called an alkene. And that's actually going to be the next type of molecule that we'll talk about. Right to the left of that, you got a benzene ring, and for now, that's our only aromatic one. Right below our aromatic compound, we have a carbonyl, and that carbonyl is right next to a nitrogen. So this arrangement of atoms is an amide, and now we want to say if it's primary, secondary, or tertiary. Well, how many carbons are coming off of that nitrogen of the amide? I already highlighted one of them, that's the carbonyl one, and it has another one right here. So this would be an example of a secondary amide where you have 2 carbons coming off the nitrogen and 1 hydrogen bonded to the nitrogen. Remember, what's not being shown on a lot of these oxygens and nitrogens are their lone pair of electrons. So nitrogen's trivalent, it has 1 lone pair when it has no formal charge. Continuing with our functional groups, right up here a little bit to the right, we have an oxygen-oxygen single bond, and that's called a peroxide. To the right and up from there, we have a carbon-carbon triple bond. Now I'm going to add this in just for now, but we have a carbon there and a carbon there. So there's one at each end of that triple bond. That's called an alkyne. To the right of that, we have a sulfur double bonded to an oxygen, and that's called a sulfoxide. Going down below that a little bit, we have a sulfur that's being flanked by 2 carbons, one here and one here, and so that's just called a sulfide. To the left of our sulfide, we have a carbonyl. And notice there's nothing but carbons on either side of it. So there's a carbon there in the blue that we highlighted, and there's another carbon on the other side of that. So when you just have a carbonyl, that's called a ketone. Down from our ketone, we have an OH group. An OH group is called an alcohol. And we want to determine if it's primary, secondary, or tertiary. So we know that the alcohol has to be bonded to a carbon there. That first carbon is called the alpha position. We want to look at with an alcohol how many carbons are coming off of the alpha position. So one here and one here. So 2 carbons coming off of the alpha position, and this is called a secondary alcohol. Just below our alcohol, we have oxygen being flanked by 1 carbon, 2 carbons. This is called an ether. And then in the very lower right corner, bottom of our molecule, C triple bond N, that is called a nitrile. So I think we found all of the functional groups in this made up molecule that I just, randomly put together. This isn't a real thing, just for practice. And now let's identify common alkyl groups and practice that as well. So using a different color here. In the upper right hand corner, I see one kind of sticking out at me. That's one of the common ones that we learned. Notice that arrangement of 4 carbons. 1, 2, 3, 4. It's attached at position number 2. That's called a sec-butyl. You can remember sec-butyl because sec is attached at the secondary position. So that's a sec-butyl group. Down here, the bottom of the molecule in the middle, this is a specific arrangement of 3 carbons. So 3 carbons is called propyl, but when it's an isomer of that, this is called an isopropyl group. And notice isopropyl is not hyphenated. So when you're using ABC order, you go by I for isopropyl, but you go by B for sec-butyl. And if you notice the little squiggly I put under the sec part of it, that's because it's italicized, and so that's what that shows. Any other common functional groups on here? I mean, we could label something like to the right of the isopropyl like this. You got a carbon here and a carbon here. It's not any like fancy arrangement. That's just called an ethyl group. You got 2 carbons coming off that chain. And you could even label something like that, but there would be a lot of those, so I'm just going to circle one. That's called a methyl group, where you just have 1 carbon. But really the isopropyl and the sec-butyl are more or less the common alkyl groups. Not that methyl and ethyl aren't, but we just use them all the time. So you really want to practice doing this and practice your naming and your spelling and being able to pick these out and identify them. Let's try one more example here. We're going to do the same thing we did last time, label all the functional groups. We'll find common alkyl groups, and then we're going to add one more component. We're going to label an sp, an sp2, and an sp3 hybridized carbon center. Okay, so let's start with the functional groups. So starting in the upper kind of left-hand corner, this arrangement of atoms where we have a carbonyl with a halogen on it. The halogen happens to be chloride. This is called an acid chloride. Kind of working just below that, we've got sulfur bonded to hydrogen. That is called a thiol. Below our thiol, we have another sulfur one, sulfur with 2 double bonds to oxygen. This is called a sulfone. And then right below that, we have an OH, which is an alcohol. We're going to look at the alpha position, which is directly attached to the alcohol, and how many carbons are coming off of that alpha position. We got 1, 2, 3. So this is called a tertiary alcohol. Working up from the alcohol a little bit, you got a carbonyl with an oxygen attached to it. This is an ester. Up from there, you got an alkyl halide coming off. So we want to determine if it's a primary, secondary, or tertiary alkyl halide based upon how many carbons are coming off of the alpha position. So just like we did for the alcohol, we got 1 carbon here and another carbon there. So 2 carbons directly bonded to that alpha position. So we would label that as a secondary alkyl halide. Up from our alkyl halide a little bit, we have a carbonyl. The functional group name for a carbonyl is called a ketone. And yes, that has something to do with the type of ketones that people talk about when they are talking about keto diets. Over to the right from there, you have a nitrogen with 3 single bonded carbons coming off of that. So nitrogen, that functional group, is an amine, not an amide, an amine. And we look at the number of carbons directly bonded to nitrogen, no alpha position. So 1, 2, 3, no hydrogens. That's going to be a tertiary amine. And to the far right, past the amine at the end, you have a carbonyl with a hydrogen coming off of that carbonyl. This is called an aldehyde. Working down from our aldehyde, we have a carbonyl with an OH group coming off of it, and this is called a carboxylic acid. Over to the left of that, right here, that's one that we already saw before, just a carbonyl, nothing but 2 carbons on either side of it. That's another ketone. To the right below that a little bit, you have a carbon-carbon triple bond. This is called an alkyne. To the left, you have a sulfur-sulfur bond flanked by carbons. This is a disulfide. You can actually even have trisulfides. but disulfide linkages are actually really important in like your hair. And below that, we got two more. We have nitrogen that's bonded to two carbons directly, and then one hydrogen. So this is going to be an amine again, but this time it's a secondary amine. And then lastly, right next to that, we got that benzene ring, and that's called aromatic. So we got all of our functional groups identified. Next, we're going to identify some common alkyl groups, just practicing with them again. So starting in the upper left, kind of by the acid chloride where we started, I see this arrangement of carbons where we got 1, 2, 3, 4. This is one way to arrange 4 carbon atoms. It's an isomer of a butyl group, and it looks like a trident. This is called a tert butyl, where tert is hyphened and the tert is italicized. That's a tert butyl group. And I see another arrangement of 4 carbons kind of in the upper right hand corner right here. So we got 1, 2, 3, 4 carbons. Notice if we numbered them 1, 2, 3, 4, it's attached at that second carbon. So this is a sec butyl group. Sec is hyphenated and italicized, just like tert. Right below the sec butyl, there's this arrangement, like a little heart of 3 carbon atoms, and this is called isopropyl. And I'm sure you can find a lot of methyl groups or ethyl groups, but we'll just focus on the ones that don't. They essentially have a name you have to kind of memorize, like the tert butyl, sec butyl, isobutyl, isopropyl. Those are the main ones you'll see. And the last part of this question asks for identifying an sp, sp2, and sp3 hybridized carbon center. So you have to know what that is in order to identify it. So an sp carbon center is going to be a carbon with a triple bond. An sp2 hybridized center is going to be a carbon with a double bond. So the triple bond would be linear, 180 degrees. The double bond would be trigonal planar, 120 degrees. And an sp3, easiest, would be a carbon that's all single bonds. And so that's going to be tetrahedral and 109.5 degrees. So let's look for, we have one alkyne we found over on the right hand side. Both of those carbons right there, they're both going to be sp hybridized. So either one of those. sp2, we had a lot of carbonyl containing carbons, so there are a ton of carbons that have a double bond, a lot of them that have double bonds to oxygen. So we can choose any one of them. We'll just go in the upper right corner of the aldehyde. That carbon right there that has a double bond, that's going to be an example of an sp2 hybridized carbon. But like I said, there's a lot of them. Like this could be another one. I'm not going to label all of them. The ketone one. Any one where you have carbon that contains a double bond. It doesn't have to be a double bond to another carbon. It can be a double bond to an oxygen also. And then lastly, sp3 carbon center, there's a ton of those as well because there's a ton of carbons that have all single bonds coming off of them. Most of the molecule is. So this right here, that carbon, that could be an example of an sp3 hybrid center. So could this, all of those. All of those carbons have only single bonds. So remember, you have to determine how many hydrogens are there that are not shown when looking at line bond structure. So this one that I identified, that has 2 hydrogens coming off because that carbon is bonded to 2 other carbons. But this one right here, that has 3 bonds to other carbons, so there's only 1 hydrogen right there. But they're still all sp3 centers because that carbon only has single bonds on it. So make sure that you get this down and that you know all of your functional groups, all their names, the spelling, and that you can identify them and draw them. And also keep practicing with your alkyl groups. Those common alkyl groups will be used in naming throughout the whole class.